Today we want to talk about one of the fundamental laws of the universe. It's the law of conservation of momentum, often just referred to as conservation of momentum for short. You may, in your science careers in high school, already have learned some conservation laws. When we talk about something being conserved in science, what we really mean is the amount you start with and the amount you end with have to match. You can't lose or gain. And it turns out in a collision, momentum is conserved. Really, really handy. But first, example 1 says this. In the collision seen below, which experiences the larger force, the truck, the car, or both the same? We're not even going to bother voting this one because we just talked about this with the bug and the bus. What's the correct answer here? A, B, or C? C. How come? Aiden, why? So if you say forces come in pairs, you can write that. If you know which Newton's law that is, which Newton's law is that? Okay, then you could either write Newton's third, or you could write forces come in pairs. Well, if the force is the same, then why is it that the car and driver are almost always worse off in the collision compared to the big truck and driver? What does smaller mass affect? Okay. Smaller m, larger a. You can write the word mass or the word acceleration if you want to, but hopefully I've taught you to abbreviate a little bit. A system like this, say 2 cars, 2 vehicles crashing, a collision, we call this a closed system. What's a closed system? It means there's no outside external forces. Nothing from off the page is pushing on it. Eric, some good examples of closed systems. Frictionless surfaces like curling rocks are a good example of a closed system when they collide. Deep intergalactic space away from any other planets. So you'd have to be out of the sun's gravitational field, out in the middle of space, away from any stars and any planets. Systems floating on the water. Water is nearly frictionless. And objects that are rolling. You do not need to memorize these closed systems. These are just some examples to get you thinking. Mika, you good? Good. Zhush. For systems that are in a closed system, the impact forces, the contact forces, well, Sophie, Newton's third rules. So forces are equal and opposite. Now here's what that means. That means momentum change is also equal and opposite. So here's a little proof. I said, look, in this collision, I know F1 equals the opposite of F2, but they're the same magnitude. Forces come in opposite pairs. And since they're both in the same collision, the time must be the same for both. And as you pointed out, force times time, why, that's impulse or change in momentum. So what does it mean to say that momentum change is equal but opposite? Suppose the car lost 20 units of momentum. What happened to the truck? Suppose the car lost 20 units of momentum, 20 kilogram meters per second. What happened to the truck? Can't have lost 20. It must have gained 20 so that the grand total stays the same. That's what impulses being equal and opposite means. That's what momentum being conserved means. Since momentum change is equal but opposite, what that means, Zana, is momentum for the system is not gained, it's not lost, it's just transferred from one object to the other. If you know the total momentum, was that yours? Really? After my earlier warning? Put it on vibrate, you're not that important, or you can put it airplane pie face down, I'll leave it to you. Zana, what that means is, for example, in a collision, if one object loses 500 kilogram meters per second, the other object must have gained 500 kilogram meters per second. Okay. Example 4. Here's a head-on collision after the collision, the car and truck end up at rest. If they ended up at rest, what was their final momentum? Why? Because momentum is what times what? Mass times velocity. Okay. Well, Mr. Dewick, if their final momentum is 0, how can you say that we didn't lose momentum during the collision? Because we ended up at 0. And you just said we don't lose momentum. It's a good question. So, Zaina, what's the final momentum? You already told me. Good. So, momentum final is 0. Here's before the collision. I'm going to use lowercase t for truck, lowercase c for car. And here's what I'm going to say. Before the collision, we have the momentum of the truck initial and the momentum of the car initial. Is that okay, Jonah? Momentum is what times what? That's change in. Momentum is what times what? Wrong line.
What's times the
That's impulse. Momentum, which is not the same as impulse. An impulse is a changing momentum, is what times what? Mass times velocity. So I'm going to argue that the momentum of the truck initial, that's the mass of the truck, velocity of the truck initial, and mass of the car, velocity of the car initial. I've got lots of subscripts there, Cole, but you're familiar with initial and final. I'm just also adding T for truck and C for car. Cole, what is the mass of the truck as a number exactly? The question told me in the picture. What's the velocity of the truck as a number exactly? And then plus, what's the mass of the car? Be very, very careful. What's the velocity of the car? And ready? What's the velocity of the car? What? Cole, what? Hey, can you do that on your calculator? What do you get? Do you get 0? Zaina, what did you say the final momentum was since we came to a stop? 0. So that we knew because it came to a stop. And I've told you momentum was conserved. Means we must have started with 0. Did we start with 0? This is why we're going to have to pay attention, Cole, to directions. Thank you for catching that. We need to let one way be positive, one way be negative. But yeah, we didn't violate any laws here. We started with a total of 0 momentum. We finished with a total of 0 momentum. Momentum was conserved. We didn't gain or lose. It was transferred from one object to the other. The car absorbed 24,000 kilogram meters per second to go with its original negative 24,000 kilogram meters per second, and that brought it to a stop. So what's the law of conservation of momentum? It says this: in a collision or explosion in a closed system, momentum is, here's the fancy word, conserved. What you start with is what you end with. This means that momentum isn't created or destroyed, not gained or lost. It's just transferred from one object to another. The law of conservation of momentum can be written in several ways. You can write it in English. The total initial momentum of the system equals the total final momentum of the system. It's unlikely that I write it in English because that's too much writing, and you've hopefully had me enough to know I'm lazy but organized. You can write it as an equation, Acacia. Momentum of object 1 initial, momentum of object 2 initial, after the collision, momentum of object 1 final, momentum of object 2 final. What is that funny symbol there? Okay, it's a sigma. What does a sigma mean in math? It's an abbrev. What's it an abbreviation for? I think you're right. The sum or the total. So this third version is saying the total momentum you start with has to equal the total momentum you finish with. Momentum is what times what, Zaina? And so you could write this first line as M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. All of those are totally fair game. Eric, which of those is the shortest, the least amount of writing? The first one, the second one, the third one, or the fourth one? Which one also has nerdy Greek letters in it? The first one, the second one, the third one, or the fourth one? Which one is it more likely that Mr. Dewick will use because A, he's a nerd, and B, it's less writing? I'm going to use the third one. Don't let it scare you. But if I see a car crash, a car collision as a question, one of the first things I'm going to write down is the law of conservation of momentum in the shortest form possible. We use the law of conservation of momentum when there's a collision or an explosion. I read that wrong. We use the law of conservation of momentum when there is a collision or an explosion. We use it whenever there is a jeune. That's a good job for the law of conservation of momentum. I have a lovely example. Let me bring out my physics toy. So we can explain that physics toy, Newton's cradle, using the law of conservation of momentum. Momentum is conserved in all the collisions. Okay, you gonna make it? Blink's getting longer and longer. Turn the page. Let's start. It says, Fahim, what does example 5 want me to find? Missing velocity. We're going to pause for a second. We got a visitor. Hang on here.
Sorry, Craig.
Fahim, again, let's ask, what are they asking me to find? Look at the picture, is there a collision? Look at the picture. Is there a collision? Yes, that's what the little doink in the middle is supposed to be. Okay. So let's ask this again. Shh. Mika, hang on. Fahim, is there a collision? Say yes. This is a job for conservation of momentum. I'm going to write the short version. I like to write something down before I jump on in because it's no longer blank. I feel better, so I'm going to write this. The sum of the momentum that you start with has to equal the sum of the momentum that you finish with. Now, look up for a second. When you type a sigma, it's supposed to look like that. But most of us, when we handwrite a sigma, we just kind of make it look like a capital M on its side. And so you're going to see, I'm going to get kind of slow. By the way, that's also where our capital letter S comes from. See it hidden in there? Wow. Yeah. So my sigmas will look like M's on their side. If you want to, you can certainly do the fancy schmancy, that one there. All right. Fahim, is there a collision? Say yes. Okay. Before the collision, what's moving? Car A, car B, both or neither? Stuck together before the collision or separate before the collision? How do I know? Because they're traveling at different velocities. Okay? We're going to write out the longest version in this first example, and then we'll start to ask where can we cut corners. So my brain would say this, Fahim. Before the collision, I have the momentum of car A initial and the momentum of car B initial. Wham! They collide. After the collision, what's moving, Fahim? Car A, car B, both, or neither? Well, definitely car B, because it says it has a velocity of what? And I'm going to guess car A, because they're asking me to find the velocity. So, after the collision, what's moving? Car A, car B, both, or neither? Stuck together or separate? Yep. The momentum of car A final and the momentum of car B final. Fahim, momentum is what times what? So the next thing I would write is mass A, velocity A initial, plus mass B, velocity B initial. Wham, they collide. Mass A, velocity A final, plus mass B, velocity B final. There's the longer version of the law of conservation of momentum. Fahim, what am I trying to find? There's 4. Which one? Final or initial? So, what am I trying to find? You know what? I'm trying to get that by itself. What side is that on? Left side or right side of the equal sign? Well, the whole left side is going to drop down like a domino then. I want to get the VA final by itself. What else am I going to do, folks? Well, Fahim, what's this MA doing to the VA final? So? What's the MBVB doing to the VA final? So? Which one am I going to do first? Reverse bad mass. Minus MBVB final. That took care of that. I'm not going to cross it out, but you can in your homework. Then what, Fahim? Sorry? Yeah, and we got to be careful, make sure we use the right mass. And then, Fahim, if you don't mind, I'm going to put the VA final over here, because that's where we're used to seeing the thing by itself. This may seem like a lot of work, but actually, I'm hoping, Fahim, it's pretty similar to what we just did in forces, and it's just more complicated plug and chug. So let's actually get our answer. I've scrolled down, Fahim. What was the mass of car A? 1,000? What was the velocity of car A? Sorry? 10? What was and now I'm just filling in, walking along this equation. What was the mass of car B? What was the velocity of car B? No, can't be. Why -2? Because you just told me VA was 10. Well, you just decided right was positive. So that means that left is what? Okay. And then there's a minus sign, and you just told me mass B was 2,000. What was velocity of B final? And make sure you're careful with your sign. Which one? 4. And then I guess all over 1,000. What's the final velocity of car A after this collision? Well, it's going to be 10,000 minus 4,000 is 6,000 minus... I think I'm getting a negative answer. Try this on your calculator, of course. Keisha, what'd you get? Negative 2? So, that's what I got in my head, I agree. Negative 2 meters per second, or 2 meters per second. How could I give that with a direction? Backwards, or left, or west, but since you said backwards, I'll use that. The question didn't specify what frame of direction they wanted me to use. If they had said east and west, then I would give my answer in terms of east and west. If they had said left and right, I would give my answer in terms of left and right. They let me pick. So I would accept two. First of all, if you said negative 2 meters per second, I would probably live with that. But 2 meters per second backwards, west, etc. Turn the page. Good stretch. Okay. Scott, my friend, looking at B, is there a collision? What are they asking me to find? Find the thing that's got a question mark next to it. Initial or final? How do you know? You're right. How do you know? Before. Okay. So what are they asking me to find, Scott? Loud and proud. Of? Yeah, okay. Do you see, looking at the picture, any changes in direction? This is, Fahim, I think what we should have done to begin with. We maybe should have started out letting one way be positive and one way be negative. So let's let to the right forward be positive. I'm going to put, if you're okay with that, Scott, a negative there. And it looks like I would put a negative there, but I would not put a negative in front of the 4. Is there a collision? Change colors, Mr. Duke. The sum of the total momentum beforehand has to equal the sum of the total momentum afterwards. That's the law of conservation of momentum. Is that the one I gave you on your formula sheet, by the way? I probably would have given you the shorter, nerdy Greek letter version, yes? Okay. Scott, before the collision, what's moving? Mass A, mass B, both or neither? Before the collision, stuck together or separate? Okay. Don't write this down, look up. Don't write this down. You could, if you wanted to, go, okay, momentum of A initial plus momentum of B initial, but let's see if we can skip a step. Scott, momentum is what times what? Okay, pick your pencils up. I'm going to go mass A, velocity A initial, plus mass B, velocity B initial. Crunch. They collide. Hey, Scott, after the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? How do you know? Different velocities. Okay, so it's going to be mass A, velocity A final after the collision, and mass B, velocity B final after the collision. And I hope you can say what we're really saying is, look, here's everything that was moving beforehand. Here's the total momentum we started with. Here's everything that was moving afterwards. Here's the total momentum we finished with. They have to be the same. That's the law of conservation of momentum. Okay. Scott, what am I trying to find? Which one? There's two. What's going to drop down like a domino then? VA initial is going to drop down like a domino? What side is the VA initial on? The left. So what side's going to drop down? The whole right side, right? M, A, V, A, final, and M, B, V, B, final. Now what? Minus this whole term, MB, yes, good. You do know. Then what? By? This is sort of like your a little version of Scott's theorem, except now we're dividing by m to get a velocity by itself in terms of momentum. And I agree with you, that equals VA initial. Let's carefully plug and chug, paying attention to our negatives and positives. Scott, what was mass A as a number? 1,000? What was velocity A final? 2? Is that right? What? Now, Scott, if this was a multiple choice question, would I have as one of the answers to pick from if you missed the negative? Would I probably put that as answer A just to really tempt you? Yeah, don't do that. And then what was mass B? Sorry? 2,000? Velocity B final? Positive. And then minus 2,000. What was velocity B initial? All divided by 1,000. You know what? I might be able to do this in my head. Race y'all. Let's see if I can do it in my head faster than you can type it in your calculator. It's going to be negative 2,000 plus 8,000, which is 6,000, minus 6,000. Oh. Do you get 0? No, Mr. Duke made a mistake. Plus Mr. Duke. Let's try that again. Negative 2,000 plus 8,000 is 6,000 plus 6,000. 12? 12? 12. Positive or negative? So if I look at this collision, Scott, I guess we're saying car A was coming in really fast. Car B coming in not so fast but heavier. They collide. After the collision, car A bounced back a little bit, car B bounced forward a little bit. Is that all right? I'm going to pause here. I think I got two more to do that I'll finish with you all tomorrow.